Hello guys, welcome to my third or whatever number video, and this time we are going to reverse engineer a laser diode, particularly a fiber coupled laser diode from Focuslight. They have a 8 watt and 950 nanometer laser diode, and these are very efficient laser diodes. Actually, they have 40%. This is the old data. The new data should be 45% conversion efficiency. And these are not very cheap. I mean, considerably cheaper than it was before, but it's still $152 each. This is the old version, which is the FCSE01, but there's a new version called the 08. The 08 version is considerably shorter and a little bit wider, generally smaller, and the pitch of the pins is only 2.54 millimeter, and besides they're pretty much the same thing. And of course, while the new package has a little bit wider operating temperature, I think it's 10 to 40 C. Besides, they're pretty much the same thing. And let's say the laser itself, the new version, I have a quote which is $152 each, and I recently bought some of them. I originally acquired two of the old version, which is the FCSE01 part number from eBay, and now since I have two new lasers to play with, and also my PCB for one project, I don't want to talk about that too much, but for a particular project, since PCB is designed for the new laser, so the old laser is pretty much no use to me, so I decided to tear down one of them and see how they build it. So we know that if we take a look at eBay, we can see that let's see, laser diode, C mount, oops, typo. You'll see that actually for its high power laser diodes, they are not that expensive. Let's say for a 10 watt laser diode, see that the diode is only $100, but this module sells for $150. So there must be something very expensive happening in the packaging part. And by the way, I got a quote from a seller that a single 3 watt laser die itself without the C-mount packaging is only $20. So to get a similar power of 8 watt, actually 9 watt, the die cost is only $60, but they're selling for $152 for the module. So it's definitely something very expensive happening in the packaging. Let's see how they build the package for such a laser diode. So let's first start with a picture. So this is pretty much the FCSE01 part number, and I cut open the top lid, which I believe is made of covar, I think. Well, pretty much because the laser itself is very sensitive to thermal expansion, and also the reliability of this kind of bonding things and soldering things is very critical, and these things are very expensive. They don't care about cost. So if I am the designer, I would like to design something that is very stable and has a very similar thermal expansion rate compared to the actual semiconductor. So covar makes sense for me, and also covar makes very nice hermetic seal. So you can see here we have some kind of glass or ceramic, and covar is actually very glass or ceramic compatible, so they can make very perfect seal. So within the module, you can see there is a hex nut, and beneath the hex nut we have I think it's made of copper or something steel maybe. The bottom of the nut is the bottom thread of the nut is actually made of steel, I believe. It's magnetic, and the part in the middle, the substrate, I think is made of copper. And then on the copper we have, I don't know what's the material, maybe Rogers or some weird material. And upon the substrate, we have the actually very tiny power device, which is the laser diode. Here we have very fine but a lot of gold wires coming from the terminal. They are actually, I think, ball bonded to the substrate, and the positive side of the input is actually the back side of the power device. And the top side of the power device is actually wire bonded to the other plane of the substrate. And that goes to another terminal. And the output of the laser diode, I was assuming there should be some kind of optics, maybe a lens or maybe 3 lenses in telescope configuration, maybe 2 lenses in telescope configuration, or another one for fixing the image, or for better collimation or some kind of things. It turns out there's no optics at all. So I would say the laser light comes from the device itself and directly goes into the fiber. Let's take some closer look. So this one is, this one is pretty much from the back of the device, and you can see that there is a little bit angle on the ferrule of the fiber, and also there's a slight angle of the power device. So why are they doing that? That's something like the APC connector. So the fiber is cut to a certain degree. Here is 8-degree angle, and so what happens is the incident light goes in this direction into the fiber, and the reflection light from the fiber goes straight out. And that means in our configuration, the reflection light coming from the fiber goes directly into this direction. Keep in mind that that's not the direction of the power device, a little bit 8-degree offset. And then the incident light came from another offset, but since we have the full reflection, so all the power goes into fiber. So they want to do that. Actually, for my application, I don't care about the reflected light, and even if there are any reflection, it will be the same wavelength from the laser. I don't care. But for some applications, people actually use this diode laser as pump light to pump some other laser source. So in that case, it's very crucial not to let the pumped or new laser coming back to the diode laser. So why that's important? Because this kind of laser diode is called Fabry-Perot laser. So what happens inside is, so here we have pretty much, let's use my picture. So the front surface and back surface, there are two surfaces, and they form a mirror. So the back mirror has 100% reflection, and the front mirror has a little bit less than 100%, let's say 95 or 99%. So the light bounces inside all the way and many times, and that forms, and also in that time, the photons excite other photons and get amplified by the semiconductor. The semiconductor itself is pretty much a optical amplifier. So how to find, and the amplifier has a certain bandwidth, and it's pretty much like a LED. So what makes laser different compared to LED is because they have the kind of the mirrors. The mirrors form a Fabry-Perot interferometer, and what that does is that selects a certain wavelength. So the different wavelength will not pass through the interferometer, and only a certain set of given a certain interval of wavelength can pass through this thing. So let's say we have a amplifier, which is almost the same thing like a LED, and that amplifies in this region. And in this region, the interferometers only has one peak, so this peak gets amplified for many times, and that forms the cohesive light output, which is a laser. So that's pretty much what happened inside the die. And as I said before, the interferometer actually has multiple bandwidth separated by a certain interval. So if the reflected light also hits one of the bandwidth region, then what happens is that the reflected light might be amplified also by this light amplifier, which will probably interfere the operation of the pump laser. So people don't really want to have the photon energy reflected directly into the we call that resonant cavity of the laser diode, and that's why we have a slightly angled configuration. Another benefit is since the incident light comes at a tilted angle, so that it reduces the air to glass reflection. I think from some data, I think it reduces that by 6% or something similar. So that's pretty much how this thing works. When we take a closer look, we can see the angle of the power device. And also here I removed the nut, the screw. And by the way, here we can see a top layer of solder and a bottom layer of solder. And apparently we have the die, so we have another layer of die attached solder. So we have the 3 layers of solder. So what they actually did is they have different melting temperatures for the 3 different solders. The bottom solder melts at lowest temperature, somewhere like 150 C. I believe it's bismuth-based solder, which melts at exactly 138 degrees C. And then above that, we have a layer of probably SAG solder. And finally, we have a layer of high temperature, I would guess it's somewhere like tin gold solder. So why they bother doing that using 3 different types solder? Because as we said before, this laser must be placed strategically in a certain angle. And you don't want the laser to float around when you are doing some different layer of packaging soldering. So this level of solder must withstand the highest temperature. So that makes sure that after we attach the semiconductor device, and in the later soldering process, the first solder will not melt, so that it is pretty much fixed at a certain position. And for the same reason, we want to make sure that when we are soldering the entire copper assembly, we want to make sure that the substrate will not move, and therefore the substrate temperature must have a higher melting point compared to the copper solder. And therefore we have 3 different temperatures for different things. And this is actually very common in power modules as well. In many high power devices, maybe IGBT or MOSFET modules, the die attachment solder has higher melting temperature compared to the other soldering temperatures. And that's to make sure that when we are reflowing for the terminals or something else, we want to make sure that the power devices, the dies themselves, will not move. And here we have another closer look at the actual die itself. You will see the die is actually very thin. It's only maybe 100 micron or even less. And you cannot see from the photo, but actually with my naked eye and very strong light, I can see actually the emitter of the device is at the very left side. I would say the aperture of the emitter is only 100 micron or less. The reason I'm saying this is because the fiber it couples to is a 105 micrometer core fiber, and that means the aperture of the emitting device even after the slow axis beam divergence must be less than 105 micrometers to ensure we have a lossless coupling. Well, there are some other factors of coupling loss, but only for this kind of loss, when we're talking about the geometry loss, to eliminate this kind of loss, we must make sure that the expansion of the divergence and also the size of the emitter must be still smaller than the core diameter. And here I actually desoldered the copper assembly, which is this. You have a closer look at the bonding wires, and also I removed the bonding wires coming from the terminal to the substrate. So at this kind of magnification, we can see the small balls, and that's called ball wire bonding. And there are other different kind of bonding that has a square shape. That's called wedge bonding. And I believe there are some other kind of bondings, but pretty much in power devices we use wedge bonding, and for microelectronics we use ball bonding. And here we can see the gold-plated part of the substrate, and the nickel-plated, I don't know if it's nickel or silver, I believe it's nickel. The nickel-plated part for die attachment, and there's another gold area for bonding. There's another small sector. I think that's gonna be some kind of a photo detector, I would say, or temperature sensor. It was not populated on this particular part number, but I think that's kind of an optional thing. So you can order the same device with option that has the sensor, and they'll charge you accordingly. And they don't have to redesign the substrate. They already put that on the substrate. So if they want to do, they simply place a die and create a wire bond, and then create other bondings to the terminal, and that's it. And here is a side view of the power device. I'm not sure if you can see that, but I can see a little bit small window here, and that's actually the emitter aperture. And all the other parts, they are not actually emitting any power. They're just passive area. And now I removed the copper part, so we now only have the substrate. We have a closer look at that thing, but it's pretty much the same photo. I'm not going to bother waste my time. And finally, I actually removed the wire bondings on the device itself. So now we are left with a very clean device. And now we can see, well, it's actually a very pretty device. I mean, technological points. It's really kind of art of engineering how people do this, and for such a long aspect ratio, it's very long device. Actually, there are some manufacturability issues, but they actually managed to build that kind of power device. Very cool. Let me see. And for the fiber connection, they actually have a rubber sleeve to protect the fiber, and apparently I removed that rubber sleeve. So a completed assembly will be a casing, and then there will be the power device assembly, wire bonding, and then we have a metal ferrule, and inside the metal ferrule we have a ceramic ferrule, and inside the ceramic ferrule we have the I believe it's gonna be a bare fiber, and then somewhere in between of this we have the tight buffer, and then finally we have a sleeve that forms the finished laser module. And as I said before, we have a certain wavelength of excited laser, and that laser emits from the right edge of the device. As I said before, the aperture is only at the very right edge, so they designed such a tilting angle and also you can see the spacing between the devices and between the device and the fiber. So they make sure that the output power shines exactly at the center of the fiber at a designed angle so that it doesn't reflect too much, and also the return light doesn't go directly into the amplifier cavity. So yeah, I would say this is pretty much, I mean, very beautiful engineering, and that looks so nice. Actually, why I'm doing this reverse engineering, because I'm recently designing a product, and since this is the single most expensive part, so I want to reduce the cost, and therefore I'm looking for designing my own actually fiber module. And also another reason I cannot use this in my final product is because look at the wire bonding. These are all inductance source. Look at that. These are all induction source, and I'm looking for very fast switching, so that's not an option. And actually, I can observe quite some spike on the terminals using a very high-speed oscilloscope. So I'm thinking, because I already have access to these laser bear dies, so I'm thinking, and also I have access to DBC process. So I'm thinking, why not build my own laser module so I can use a DBC and mount the power devices and mount my control device, which is gonna be an ASIC implemented using a custom IC process, and couple them very closely, and also place the coupling capacitors very closely, so we have a very low inductance path, and then we can use our own fiber and ferrule assembly, so that eventually we will have a same or even better performance at much lower price. And also, this is an 8-watt model, and well, we do not need that kind of power. We only need somewhere like 3 or 4 watt, but they don't sell that very low power devices at much lower price. They're pretty much the same price. So I'm thinking, well, since we have access to lower power dies at much lower price, so why not do that? And that's pretty much why we are reverse engineering this thing. I hope you guys like this video, and please, well, if you want to subscribe, but I don't really have too many videos, but at least a thumbs up if you find this video very interesting and very useful for you. And thank you for watching this video.